Have you ever wondered what could happen if we combine AI and quantum computers? It's both exciting and scary. Quantum computers are incredibly powerful and can solve complex problems much faster than regular computers. But there's a catch. Renowned physicist Michio Kaku has discovered something terrifying, and it could lead to the extinction of humanity. Join us as we explore the world of quantum computers and AI, their revolutionary potential, and the shocking warning from Michio Kaku. Quantum computers are exceptional computers that revolutionize computing by operating on the principles of quantum mechanics. Unlike classical computers that use bits to store and process information, quantum computers utilize quantum bits, which are commonly called qubits. While classical bits can only be in two states, 0 or 1, qubits possess the incredible ability of superposition. This means that a qubit can exist in multiple states simultaneously, representing both 0 and 1 at the same time. This is not just a little advancement in the basis of computation. We are talking about a large leap that provides possibilities for solving highly complex problems that our modern computers are limited to. The power of quantum computers lies in their capacity for parallel computation. By exploring different states and possibilities simultaneously, they can potentially solve specific problems much faster than classical computers. Undoubtedly, there is a widespread debate about the use of this revolutionary system. At first, you could liken it to the regular developments we are making on classical computers, increasing the processing power of a single chip. But the argument here is quite different. The improvement comes from the basic unit of computing. Quantum bits outperform classical bits, and this leads to the wide gap between the processing power of quantum computers and conventional computer systems. Now, let's walk through the history of this invention. Quantum computers have a rich history dating back to the early 1980s when physicist Richard Feynman introduced the revolutionary concept of quantum computation. Feynman envisioned a new kind of computer that could leverage the principles of quantum mechanics to tackle complex problems beyond the capabilities of classical machines. However, it wasn't until the 1990s that significant breakthroughs in this field began to emerge. Back in 1994, a mathematician named Peter Shor, working at Bell Labs, unveiled an algorithm that sent shockwaves through the scientific community. This algorithm was a game-changer for quantum computers because it had an incredible ability to solve problems that were previously thought unsolvable by classical methods. To efficiently factor large numbers. Now, you might be wondering why factoring numbers is such a big deal. Well, it turns out that factoring plays a crucial role in many encryption methods used to protect sensitive information in our digital world today. Shor's algorithm opened up a whole new realm of possibilities and sparked both excitement and concerns among scientists. It showed how powerful quantum computers could be in breaking the encryption systems we rely on. So, throughout the 1990s and early 2000s, researchers rolled up their sleeves and started exploring different ways to build practical quantum computers. One of the most promising approaches involved tinkering with individual atoms or ions to act as qubits, which are the building blocks of quantum computers and are the fundamental units of information in quantum computing. In 2001, a group of scientists at IBM achieved a major breakthrough. They successfully demonstrated the concept of quantum computing by using nuclear magnetic resonance to control qubits. Think of it as an eureka moment in the world of science. This achievement showed that quantum computation was not just a wild idea but something that could actually work. It lit a fire under researchers, pushing them to progress even more. As time went on, scientists made incredible strides in developing stronger and more reliable qubit systems. They explored different types of qubits, like superconducting circuits and trapped ions, each with its own set of advantages and challenges. They were trying out different tools in a quantum toolbox to see which worked best. All these advancements paved the way for the construction of increasingly powerful quantum computers. The number of qubits kept growing, allowing for more complex calculations and simulations. It's like going from a basic calculator to a supercomputer. Later in 2013, something great happened. Google and NASA joined forces to create a quantum computer called the D-Wave 2. Picture it as a high-tech powerhouse that was going to be housed at NASA's Ames Research Center. But, guess what? A government shutdown came along and threw a wrench in the works. It disrupted the project and stopped the quantum computer from reaching its full potential. Why? Well, it had to do with worries about the potential risks that could come from using such an advanced computing system. Even though the computer was up and running, the shutdown put a halt to further progress and plans until NASA could get back on track. Fast forward to 2019, and Google was in the headlines again, blowing minds left and right. They achieved what's called quantum supremacy with their super-duper quantum processor called Sycamore. What does that mean? Well, they tackled a complex math problem that would have taken classical computers thousands of years to solve. And more interestingly, Google's team cracked it in the blink of an eye. This accomplishment showed just how incredibly powerful quantum computers can be for specific tasks. It got everyone excited and pumped up about the potential of this technology, which led to even more investment in the field. Then, in 2020, IBM dropped a bombshell. They introduced the IBM Q System 1, the very first fully integrated quantum computer designed for commercial use. It was like the ultimate dream come true for making quantum computers accessible and practical in the real world. Just imagine having a quantum computer right at your fingertips, ready to tackle all sorts of mind-bending problems. All these advancements in quantum computing caught the attention of governments and industries worldwide. They couldn't resist the allure of this transformative technology. So, they started pouring in big bucks to support quantum research initiatives. They even set up fancy-schmancy quantum research centers and labs that brought together smart folks from academia, industry, and government agencies. Although the discovery and full adoption of quantum computers are still in their infancy, there are theories that claim that quantum computers, or perhaps systems that operate using the logic of quantum computing, might have been in existence in our universe already. We are talking about black holes. According to modern scientists, the existence of extraterrestrial intelligent life is believed to be probable. One intriguing possibility is that they might be utilizing black holes as quantum computers, which could explain why we haven't detected their presence. This scenario is related to the Fermi paradox, which has puzzled astronomers and cosmologists for years. Despite the high likelihood of life existing elsewhere in the universe, we are yet to find widespread evidence of it. The Hart-Tipler conjecture offers an explanation for this paradox. If advanced extraterrestrial civilizations have emerged in our galaxy, we should observe signs of their activity throughout. This conjecture aims to address the question of why we have not encountered clear indications of extraterrestrial civilizations despite the probabilities. In connection to this line of debate, Michio Kaku suggests the intriguing notion of an extraterrestrial superhighway beyond Earth. A laser-based network through which billions of alien beings may be traversing the galaxy. However, determining the existence of such a phenomenon requires us to question our technological capabilities. We currently lack the means to definitively prove or disprove the existence of this hypothetical superhighway, which could potentially be situated right outside the Earth's orbit. As quantum computing progresses, researchers are busy tackling the remaining technical challenges and striving to scale up quantum systems. The ultimate goal is to unleash the true power of quantum computers, enabling them to beat problems that classical machines find incredibly difficult. We're talking about highly sophisticated tasks like large-scale optimization, complex simulations, and supercharged machine learning. Since qubits act like they have a split personality, but in a good way, their superposition property allows quantum computers to perform parallel computations and explore multiple possibilities simultaneously. It's like having an army of tiny workers tackling different tasks all at once. But here's the catch: to make quantum computing a reality, we need to manipulate and control those qubits effectively. That's where various physical systems come into play. Think atoms, ions, superconducting circuits, or even photons. These systems are carefully crafted and engineered to preserve the delicate quantum states of the qubits, allowing us to perform operations on them. When it comes to crunching numbers in the quantum world, we have something similar to classical logic gates called quantum gates. These gates are like the conductors of a quantum symphony. They dance and manipulate the quantum states of qubits to carry out specific computations. By applying a sequence of these gates to a group of qubits, we can run quantum algorithms and solve difficult problems. But there's more. Quantum computing has another edge characteristic: quantum entanglement. It's like the BFF mode for qubits. When qubits become entangled, their fates become intertwined, regardless of how far apart they are. It's like they're in constant communication, no matter the physical distance. Einstein once called this spooky action at a distance. We like to think of it as a superpower. The beauty of entanglement is that it allows qubits within a quantum computer to establish intricate relationships. They can work together as a dream team, processing vast amounts of information simultaneously. This gives quantum computers additional potential to solve certain problems way faster than classical computers. It's like they have a turbo boost for computational tasks. So, with qubits, superposition, gates, and entanglement on the side, the future of quantum computing looks bright. They have shown impressive performance in many areas where classical computers struggle. For example, they're wizards at complex optimization, super speedy at factorizing those big numbers, pros at simulating quantum systems, and even masters of advanced machine learning tasks. One cool application of quantum computers is in the realm of optimization. They can come to the rescue when it comes to solving real-world problems like figuring out the best routes, managing supply chains efficiently, or allocating resources smartly. It's like having a genius advisor who knows all the tricks to optimize things and make our lives easier. But, hey, there's another side to the quantum coin. When it comes to cryptography, quantum computing has caused quite a stir. Many cryptographic systems rely on the difficulty of factoring in those gigantic numbers. And guess what? Quantum computers can breeze through that task thanks to a nifty algorithm called Shor's algorithm. They have the key to unlock encryption secrets in a flash. Now, this brings up a big concern. As quantum computers continue to evolve and become more powerful, they pose a potential threat to our beloved cryptographic systems. But fear not. Researchers are on the case, actively developing what they call quantum-resistant cryptographic algorithms. These algorithms are like secret shields that can withstand attacks from quantum computers. They're building them with fancy techniques like lattice-based and code-based cryptography to ensure the long-term security of our digital infrastructure. Quantum computers also hold promise in simulating quantum systems. Classical computers struggle to accurately simulate the behavior of quantum particles at the microscopic level due to the complexities of quantum mechanics. This limitation has been evident in many simulation systems from space exploration to simulate events across the cosmos, especially those related to the microscopic details. Classical computers have not been the best in performance in terms of accuracy and precision. Also, in fields like medicine, simulations aimed at understanding the full functioning of the human body have been limited by the available computational power and precision in many cases. In contrast, quantum computers are naturally suited for simulating the behaviors of tiny particles and quantum phenomena. By emulating atoms, molecules, and materials, quantum computers can provide valuable insights into chemical reactions, material properties, and the behavior of complex quantum systems. This capability has significant implications. For drug discovery, where quantum simulations can accelerate the search for new drugs and optimize molecular interactions, potentially transforming the pharmaceutical industry. Now, let's talk about machine learning and artificial intelligence. Quantum computers are here to shake things up and bring a whole new level of awesomeness to the table. According to the brilliant mind of physicist Michio Kaku, these quantum machines have the power to revolutionize the AI landscape. We've come a long way in creating smart and sophisticated ones, like OpenAI's very own ChatGPT. They're impressive at generating text that sounds like it's coming from a real human. But here's the thing, they still have their limits. These chatbots rely on recognizing patterns in the training data rather than truly understanding the meaning behind the words, and you know what that means? It can lead to misinformation. The bright minds of experts like Michio Kaku and Geoffrey Hinton have raised some serious ethical concerns about these AI systems in general. However, quantum computing can address some of these limitations by leveraging the power of qubits. Entangled qubits can instantly influence each other, enhancing computational efficiency, while quantum interference can guide quantum systems toward optimal solutions. These unique capabilities make quantum computers well-suited for solving these complex problems. Integrating quantum computing into AI could have transformative implications. Quantum computers' exponential speed could accelerate machine learning model training and enhance natural language processing. They could act as powerful fact-checkers, ensuring accurate information. Quantum computers have the potential to weed out false information, providing a valuable check for AI software. However, this might come in the form of a trade-off. Integrating quantum computing with AI also brings risks to data security, as quantum computers can potentially break current encryption methods. Within the next 5 to 10 years, quantum computing is expected to disrupt encryption as we know it today. It is essential to protect quantum computing innovations through patents to safeguard their advancements. Patents not only foster innovation but also grant inventors exclusive rights to their intellectual property. While the United States and China currently lead in quantum computing patents, other countries are striving to become leaders in the field. Quantum key distribution systems are very cool areas of research. But they face some challenges that make it hard for them to be widely used. Things like compatibility issues, high costs, and the need for specialized skills can be real roadblocks. However, with the rise of quantum computing, we might see a day when regular AI chatbots are replaced by quantum-powered ones. These new systems are lightning-fast, super efficient, and can double-check information for accuracy. They're so great at handling complex tasks, understanding context, and giving you spot-on responses. In the world of materials science, quantum computers have the potential to shake things up in a big way. They could totally revolutionize how we discover and design new materials with sophisticated properties. By doing fancy quantum simulations, these computers can predict how materials behave and their special characteristics. This is a huge help for experimental research. Imagine if we could make solar cells that are way more efficient, super strong yet light materials for spaceships, or even innovative catalysts for converting and storing energy. Quantum computers could make all of that possible, and there's more. The financial sector can also benefit from the quantum bandwagon to improve all sorts of tasks. Quantum computers can analyze tons of data to optimize investment portfolios, assess risks, and catch those sneaky fraudsters. They can develop even better solutions with their superpowers of handling complex calculations. That means smarter strategies for managing risks and more effective ways of catching the bad guys. Plus, we can simulate financial systems and get insights into how markets behave using fancy quantum algorithms like the quantum Monte Carlo algorithm. Quantum computers also have the potential to tackle challenges in astrophysics, cosmology, and particle physics. They can simulate the universe's early stages and help us understand the fundamental laws of nature. They can assist in the hunt for new particles, analyze the structure of the cosmos on a massive scale, and even simulate how black holes do their thing. It's like having a backstage pass to the secrets of the universe. With quantum computers, scientific research can go faster than ever, and we might uncover several discoveries that were once way out of our reach. Although the potential of quantum computers is vast, their widespread adoption faces significant challenges. Constructing practical and reliable quantum computers is a complex engineering feat due to the sensitivity of quantum systems to noise and environmental disturbances. Maintaining the delicate quantum states of qubits, the fundamental units of quantum information, proves challenging. Achieving progress in error correction and qubit stability is essential. The complexity involved in developing scalable quantum systems raises doubts about the feasibility of large-scale practical quantum computers. Moreover, the applicability of quantum computers is limited. While they excel in certain computational tasks, they are not superior for all types of problems. Classical computers continue to be more efficient and practical for everyday computing needs. Scientists stress the importance of managing expectations and focusing on problem domains where quantum computers can provide tangible advantages. This selective approach ensures that resources are allocated wisely, developing quantum computing to complement classical computing instead of replacing it entirely. By focusing on leveraging quantum computers where they can provide significant benefits, wise allocation of resources and maximizing the potential of both types of computers will be optimal. Efficient quantum algorithm development poses its own challenges. Researchers are actively working on designing algorithms that harness the unique properties of quantum systems, majorly the quantum parallelism and quantum entanglement. However, finding suitable quantum algorithms for specific tasks remains a complex and ongoing research endeavor. Careful exploration and understanding of the capabilities and limitations of quantum algorithms are crucial to harness the power of quantum computers fully. Also, the ethical concerns regarding the potential impact of quantum computers on encryption and people's privacy really bother experts about the wide use of these systems. Since quantum computing could break current encryption methods, there is a need for standardization and more complex encryption techniques to eliminate privacy risks before the general adoption of quantum computers. Additionally, since quantum computing can have significant implications for artificial intelligence and machine learning as we know it today, it is crucial to utilize quantum computers in a manner that upholds privacy and security, ensuring responsible use. However, just like any other invention, quantum computers should not be too difficult to handle once rules are set for their regulated use. By addressing technical challenges, focusing on appropriate applications, and considering ethics, we can responsibly navigate the potential of quantum computers and harness their benefits while safeguarding privacy and societal values. So, in simpler terms, quantum supremacy has been achieved, meaning that quantum computers can outperform digital computers in certain problems. However, there are concerns raised by physicist Michio Kaku regarding the combination of quantum computers and AI. The danger lies in the fact that AI chatbots lack the ability to distinguish between correct and incorrect information, posing risks if not regulated by laws. According to physicist Brian Greene, it is plausible that highly advanced civilizations may self-destruct, offering a possible explanation for the Fermi paradox. If life exists beyond Earth, why haven't we encountered it? The reasoning is that civilizations capable of interstellar travel may have annihilated themselves before reaching us. Tragically, this scenario aligns with historical events on our own planet. We can't be too careful. A high-level computing system like quantum computers should be cautiously linked with AI in a way that we can control. Considering these uncertainties and potential risks, is it wise to grant control to machines whose capabilities remain uncertain? We must weigh the dangers and make informed decisions despite the allure of technological advancements.